More minutes. I'm going to start a recording as well. So.
Okay, I've kicked off the recording.
Excellent. Welcome everybody to our second virtual meetup event, actually cross meetup group event. The pro topic is Python for Finance. I'm excited that we have again a pretty exciting lineup today with two talks. More on that where we cover the agenda. The meetup, the virtual meetup, is hosted by Python Quants as well as by Refinitiv. Jason is also with me. Jason will today take the questions from the panel. We'll sort them through, and we will have, after each talk, let's say about 5 to 10 minutes, where we will go through the questions. I have prepared here a quick introduction to today's meetup. You see the agenda here. I would spend like a few minutes only during the introduction. Then we will have the first talk by Dr. Alexander Tsyplikhin about accelerate financial modeling using IPUs and Poplar via standard ML machine learning frameworks like TensorFlow. Thomas Wiecki, Dr. Thomas Wiecki will talk about Bayesian modeling using COVID-19 data. So very current and topic of interest, I guess, to everybody. Again, we will have Q&A sessions after each talk, but feel free to post your questions anytime during the talks. So we will collect them, and we will then have at the end Q&A session. And we will close with a few words. First of all, I want to welcome everybody from around the world. So I saw that we have people from Peru, from Asia, from Europe, basically from all over the world, which is at least one of the exciting elements of having a virtual meetup group event, that we can host so many people from so many different places. We have meetup groups in London, New York, Berlin, Frankfurt, Paris, and where I live in the Saarland area, southwest Germany. But I'm pretty sure that some others might have joined us from many different places. Of course, the meetup groups are open, and we can only encourage you to maybe forward the meetup group information to colleagues or friends. In these days where we do virtual meetup events, you don't need to necessarily live in London, for example, where we have the biggest group with more than 3,000 people to attend a live event. This can be done online, and I think it's for everybody quite exciting. Here, a quick view or overview of the groups that we have. The Python Quant Finance group in London is the oldest one that we run. It has more than 3,000 members. I think it's one of the largest groups of its kind around the world. Maybe not only in the niche Python for Finance or Quant Finance, but also as a Python group. I think we are kind of like one of the larger ones. We have another group in New York, which is called AI in Finance and Algo Trading. And here we started quite a bit later, to be precise, last year only. And the group is growing here as well. And there are other groups, one in Berlin, Germany. That's the second oldest, longest running one that I have in Berlin. Welcome from that city as well, and from this group with more than 500 members in Frankfurt as well, which is basically closest to where I live, with a membership of 220 plus that we are currently having, and we are increasing the numbers around the world, and we're pretty happy about that. Paris is also a group with 300 members. Also here we see some increase, which makes us, of course, happy about algorithmic trading and artificial intelligence. That's the name of this particular group. Last but not least, the closest one, this is where I live, in the Saarland area, which is more like a general Python group, not that much focused on the finance side of things. But still, we have many Python fans here in the Saarland area, but also in Luxembourg, of course, where we have another financial hub in Europe. Yeah, we are already all set for the first talk by Alexander. I'm pretty much looking forward to it because speed has always been an important topic in the financial industry, and with ever increasing data that we have available in terms of the traditional V's like volume, velocity, and variety. It has become even more important to be able to process all that data in a fast fashion, in particular when you apply deep learning approaches such as neural networks, which we all know are quite compute intensive. Therefore, I'm looking forward to the talk by Alexander, and we are now handing over so that he can share his screen and can get started with the talk. Jason, will you give him presenter rights? I can do it as well. So,
Okay, I've given him. There you go.
here we go.
Great.
Alex is yours.
Thank you, Yves. I'm excited to be here. Can you hear me?
Yeah, all sounds good. We can see and hear.
Great. So I'm Alex. I'm a senior AI engineer at Graphcore. I'll try to talk about financial modeling and how it can be accelerated with IPUs, which stands for Intelligence Processing Unit, a processor that Graphcore has created, and then TensorFlow. So Graphcore was founded about 4 years ago. We have created Intelligence Processing Unit, and we've been growing quite rapidly in the last few years. We are now over 400 people globally, with the offices in the US, in Europe, and also in Asia. You can see on the tiny map here. We have raised over $450 million from quite renowned investors. So we're happy to be one of the leading players on the market. And we are a semiconductor company. We have built a chip. So we are competing with companies like the GPU companies around there. And we are happy to have some interesting customers like Citadel, for example, that has shared this quote: IPUs novel architecture is already enabling Citadel to explore new techniques that have been inefficient or simply not possible before. And Carmot Capital, a hedge fund in San Francisco Bay Area, says that they are getting speed ups that are very significant with our processors. So as a summary, in finance, we are seeing that the models dealing with prices, for example, are typically oversimplified because companies want very low latency and the data is very noisy and they want to not overfit to that. IPUs, our processor, are enabling more complex, more advanced, powerful models to run much faster. So companies are getting deeper insights and are able to make better decisions in shorter time, both human scale and microsecond scale. When the founding team was envisioning the processor, they have seen that machine learning is quite different as a computational workload from HPC. There is a lot of parallelism in neural networks, lots of connections, millions or now billions. There is a lot of sparsity in those connections. Not everything is connected to everything else. You do not need for machine learning double precision compute, and you can easily go with floating point 16, so half precision. And it's the ensemble of these low precision operations that help you produce highly precise prediction. There is a lot of model parameter reuse for convolutions or for recurrence. For example, you can load your model once and reuse the parameters for many inferences, for example. And then the computational graph structure is typically static. You do not have to rewire your connections for a given sample. You can leverage that. And then noise is very beneficial in a form of dropout or what's called stochastic grounding. So we have tried to embed all of these aspects and create a chip that will be efficient for this kind of workload from scratch, from ground up. So unlike CPUs that are geared and very good at scalar operations, and GPUs that are great at vectors and matrices. IPUs are centered around the graphs. And the two main differences in the architecture, if you are asking how IPU is different from GPU or TPU, would be, number one, the code and the data on the IPU are always in SRAM, which is really, really fast. It's 50% faster than HBM2 of GPUs. So for machine learning, that means that you can load your model on the chip, an LSTM, for example, and roll it back in time during training and leverage this very fast memory. So the speedups for LSTMs are significant. Number two, the programs, the threads running on the processor in parallel are independent, unlike GPUs that have a single instruction multiple data paradigm. So they apply the same instruction to a large vector of data. With this, with independence, you can basically put separate algorithms on separate threads. You can be efficient. We are efficient at batch size 1, for example. And then we have Poplar SDK, which is our framework to natively and easily support computations for graphs. If you start with higher level frameworks, such as TensorFlow and others listed here, Onyx, PyTorch, the graph produced and built in TensorFlow gets ingested by Poplar, which is our software stack, and then executed on the accelerator cards that have processors shown here below. Inside of Poplar, we have several blocks, libraries, visualization and debugging tools, compilers, and execution engines that work together and that have been built and designed together with the hardware. So it's software and hardware co-designed to leverage each other's powers. The program can be translated from GPUs or CPUs to IPUs quite simply. And this is an example. So this is a very simple CNN model dealing with CFAR10 data on the GPU on the left-hand side, and then what it looks like on the IPU on the right-hand side. So the changes here are quite minimal. You want to import specific Python modules to target the IPU, then switch to the optimized model class in Keras to construct your model. And what it does, it optimizes the execution of the training or inference loop on the device. And then finally, number 3, you configure the IPU system and you kick off the execution in the on the IPU, saying explicitly pointing to the system that this part of the model has to be placed on the IPU. Now, if you try to run these two examples in parallel, on the left-hand side, I have P3 2x large in AWS. On the right-hand side, the IPU machine, IPU server. So I execute both of them, and you can see that it would move faster for the IPU. So I can get a trained model faster, I can train more frequently, I can get predictions and insights faster. And this is a simplistic model that was precompiled for the IPU. Compilation would take a few seconds as well. This is the general architecture, simplified view for the processor. The tiny red squares are compute cores, and the blue rectangles are memory. So every core has memory which is local and private to that core. We do not have shared memory. We do not have memory hierarchy. The bandwidth between the memory and the compute is 45 terabytes per second. Each chip has 300 megabytes of very fast memory, and to fit and run larger models such as BERT, you are able to connect many chips together using IPU links that are shown here on the right bottom side of the slide. And there are many other aspects that probably are less relevant to today's talk, but I'll be happy to answer any questions here. So the chip actually runs at half the power of a GPU. So one IPU consumes 150 watts, and thus we are able to put two chips on one accelerator card. And the chips are connected together inside the card, delivering 200 teraflops per second of peak mixed precision compute. And then you can see these links going up of the card to connect chips across the cards to form a large accelerator. So for financial modeling, this would mean that for inference, you are able to make decisions with lower latency using models of greater complexity, including running backtesting faster. And for training, you can move your research forward faster, experimenting with new model architectures. And you can use new models, like probabilistic models, to avoid overfitting and account for noise. So with these speedups, you can do retraining more frequently, not overnight, but every few minutes, for example, and then change your trading paradigms. Well, a few numbers that I'll be mentioning here would be LSTMs, related to LSTMs, non-vectorizable models, MCMC, Markov chain, Monte Carlo, and then reinforcement learning. For LSTM inference, on this chart, you can see that the x-axis shows latency in milliseconds, and the y-axis shows throughput. The green chart is the GPU consuming 300 watts, different batch sizes. So the fastest this GPU can do at batch size 1, at the same latency, we are able to run batch size 256. So our throughput is 300 times more, which is beneficial for problems or for use cases such as alpha estimation, backtesting, and future generation in some cases. Some funds are using LSTMs for feature generation. If you need to go as fast as you can, making decisions faster, you would go batch size 1 on the IPU as well, and then you have 3.7 lower latency and also 7.4 higher throughput, because we just have two chips on the card. We can put two samples in parallel and process those. So another aspect that is important for algorithmic trading is independency of the programs on the chip. And this is used for feature generation and for predictions. Imagine if you have different algorithms that generate different features for your trading. It's impossible to vectorize this case typically. So IPU is different. You can put these different algorithms in form of codelets on separate threads and just run them in parallel. Instead of vectorization, you leverage parallelization on the processor. And same with models like sparse tree-based models like sparse random forests. It's very, very hard to vectorize these models. And on the IPU, you can simply put separate trees on separate threads and leverage parallelization. So the speedups for sparse random forests are very interesting. Now, For alpha estimation, for signal extraction from the data of prices and returns, companies tend to use linear models because the data is very noisy, and if you go with the more complex model, you risk in overfitting to the noise. So to deal with that, one of the very interesting solutions is to use probabilistic models such as methods such as Markov chain Monte Carlo, because it helps you not to overfit to the data. It kind of injects and leverages this noise, injects it in the model itself, because the model weights in this case are actually distributions, and the predictions are distributions over potential outcomes. So we can be efficient dealing with noisy data without overfitting and still handle non-linearities in the data. And this is important because the returns and prices are obviously dependent, and linear models that assume independency are much less relevant in this case. And MCMC has been long considered too computationally expensive because it runs for a very long time. Like reasonably complex models run for a very long time on CPUs or GPUs. For a model which is a neural network of 3 layers, this custom implementation, which is not TensorFlow, it's C++ and lower level Poplar implementation. It has reduced time to train from 2 hours to 4.5 minutes, in this case, by running just on one IPU, so half the power compared to the GPU. And then with the plain TensorFlow probability, so out of the box speed up for 2 IPUs, so same power consumption, 300 watts versus GPU 300 watts. Another customer was able to reduce runtime from 53 hours to 3.5 hours. So it is a dramatic change in performance, 15 times lower time to result. And for MCMC, I'll walk through the code and invite you to experiment with this method as well for your data and your case. For risk estimation and portfolio generation, after you have estimated your alpha, it is important and very beneficial if you can leverage so-called neoclassical risk factors, such as latent or higher moment and non-linear risk factors. And it's very hard because of the same things. The data is very noisy, and what is typically used is robust SVD kind of algorithms, so linear algorithms trying to extract linear relationships. With variation autoencoder, for example, as a model, you can try and capture non-linear relationships between the channels, the prices of in your data, and extract latent risk factors that are non-linear. And some companies are doing that, getting over 4x speed up in terms of time to train on an IPU. Then when you have constructed your portfolio, you want to manage it. And some companies are using reinforcement learning for that. And Eve had mentioned this during the previous meetup. So for reinforcement learning training, the speedups are also significant, up to 13 times higher throughput. And then there is also, of course, alternative data, such as news, tweets, and then satellite images. So for that, IPUs are also good. For BERT, we are one of the 3 companies on the planet to be able to train BERT, as well as GPUs. And for inference, we are faster in terms of throughput at the same lowest latency. For computer vision models that are more future-looking, ResNext, for example, and grouped convolutions, the kernel of group convolution runs up to 100 times faster on the IPU compared to the GPU. And overall predictions for ResNext are also done at a higher throughput and lower latency on the IPU. An interesting paper that Citadel has released in December last year, so half a year ago, is published on Archive, and it goes into the details of the IPU architecture and how it compares to other processors, and how the internal structures are functioning at what speeds as measured during Citadel's experiments. So I suggest that you take a look at this paper. There is a lot of material about the processor and the programming approach to the processor on our website, graphcore.ai. So you can navigate to our website and start reading about the IPUs. And the IPUs are available in a form of these chassis that have 8 IPU cards, so 16 IPUs total, connected together. And they are in Microsoft Azure, actually, in the cloud. So we are the first startup that has put our chips in a hyperscale cloud, which there are 3. So very excited about that. There is a preview going on, and you can navigate to Microsoft's website and sign up for the preview currently. Some of the companies in finance are very, very sensitive to public clouds. So Zero-Scale Cloud is an alternative, provides bare metal, shared nothing environment, air-gapped, and physically isolated. So different approach to the cloud, valuable in some cases. So we hope that innovators like yourself will be able to create next breakthroughs in machine intelligence, new kernels, new models, new kinds of layers. And this is the purpose of our existence. Do something better, do something different, and enable innovation in a different way. The next thing I wanted to show is the code for MCMC model. It's available on our GitHub repository. If you go to GitHub Graphcore examples, we have a bunch of things that are interesting to take a look at. Among the code examples in TensorFlow, you will see MCMC folder and this MCMC TensorFlow probability file. So I wanted to quickly walk through this code to maybe encourage you and to explore MCMC as a method on your data and see if it can bring speed ups to you. Let me switch to this window instead. So very quickly, what happens in this code, and this is the non-IPU implementation, so before porting it to the IPU, we define model or execution parameters. We would want to do 800 steps to produce results and do 100 burn-in steps. Then we load and slightly pre-process the data about returns, or sorry, it's features in this case, and then returns as well. So we observe some features and returns, and we want to predict future returns for unobserved data. Then we configure TensorFlow and GPU system a little bit, following by constructing the model. So it's a 3-layer neural network in this case, not very complex. And then we put together this function to construct the log likelihood for MCMC to enable us to sample from the posterior distribution over the weights of the model based on the observed data. So it's happening in this model log prob function. Basically, we are connecting the observations and the predictions of the model, and we allow for some noise between those. Noise of predicted or the shape that we think is relevant for this situation. And then a very simple thing happens. We initialize the state, the initial weights, state of the chain with zeros. And then we instantiate the sampler, the MCMC chain that produces the results to us in the session.run. For the changes for the IPU are very similar to what we have seen on a slide in Keras, importing the modules for the IPU system. Then we do not need this GPU option. We can get rid of that. Then we say explicitly that this part of the graph we want to put on the IPU. So IPU device 0 is what we mention here. We wrap the sampling part of the graph into a function and we compile this function with the IPU compiler to make it more optimal, because the compiler optimizes the graph as well. We configure the IPU system and we execute the sampling. So very simple. With MCMC, what I'm showing on in this comparison, the model benefits from having separate chains that was running separately and independently from each other. It ends up generalizing better. So you can leverage several IPUs and launch a separate chain on each of the IPUs and then combine the samples from these separate chains. They will explore different areas in the space of model parameters. So to do that, I slightly change the program and instead of putting the graph on one IPU, I make it dynamic. I'll allocate different scopes, TensorFlow scopes, to different IPUs. So each IPU will run a separate graph with MCMC sampling, which is done here in this loop. So for every IPU, I instantiate the relevant scope for relevant IPU number, and I put the graph inside this scope. I configure the IPU system slightly differently. I feed a list with several ones in it. So it will be several separate devices with one IPU each. And then I execute this combined TensorFlow up, and I concatenate the results to produce the samples. And this is the code, the multi-chip code that you will find in this repository. So I'll be happy to answer any questions about the code or the IPU and the company. This is the end of the presentation. My email address is shown on the slide, alext@graphcore.ai. So thank you very much.
Wonderful. Thank you so much, Alex. That was a super interesting presentation. We got a couple of questions that we just come in. Basically, from Jonathan, who's saying, you mentioned that the different batch sizes gave different performances. Is there any batch size where GPUs turned out to be better than IPUs?
For some models, yes. For typical, well, for very large models that leverage multiplying huge matrices, GPUs are highly optimized for that. So GPUs are made for multiplying very large dense matrices. So they might be able to handle batch sizes that are larger than IPUs can. And the throughput can be higher in this case in terms of samples per second. But the researchers have shown that for large batch sizes, the convergence is worse. You need more epochs to converge with large batch sizes. And in this case, for example, the throughput that we get is higher even at very high batch sizes that GPUs can do.
Perfect. I think that's a very good answer. Then we've got so sort of like in the sort of real-time space. I suppose this Klaus is asking, for which timeframes or candle sizes would I be able to benefit from this architecture? I suppose that's to do with maybe running sort of like in real time or near real time. How have you seen maybe some of these been implemented, or how some of the other people you mentioned, Citadel, using this kind of stuff? Is it for the real time side, or is it for different types of classification or tasks, that kind of thing?
Yeah, I cannot comment on Citadel's use cases definitely, but the ranges, the time ranges for inference, for example, are similar to other PCIe-based accelerators. So it's microsecond scale.
Okay, great. So, okay, perfect. And sorry, just bear with me. So I've lost my screen. Yeah, and how does like an IPU differ to or compare to a TPU?
So TPU is very similar to GPU in terms of the concept behind the architecture. TPUs are great at multiplying huge dense matrices. The NetMol block of the TPU is 128 by 128. So smaller matrices, small batch sizes will be quite inefficient on TPU. There are models that Google has created that are very efficient on a TPU, and BERT is one of the examples there. So it was built for TPU enabled by TPUs, and BERT is basically a sequence of huge netmols. And we have shown that IPUs can do just as fine as GPUs on that, though it's not our sweet spot. It's not what our mission is. We want to enable something new and different.
Great. Awesome. Thanks very much for that. We've got, so I know you mentioned that you currently have like a test environment in Azure or Azure. And somebody's asking, can you please, do you have any IPU systems in AWS cloud, or planned in AWS? Maybe not now, probably, but maybe planned.
We do not. We do not.
No? Okay.
So it's
only
Azure for now.
And we have another question, which was, what kind of GPU was used during the comparison of your latency, Rupert?
Yeah.
What was the card?
Unfortunately,
I think you had it at the bottom somewhere.
It's the very advanced, the most advanced as of yesterday GPU, consuming 300 watts. Unfortunately, I'm not allowed to say what model is that exactly based on the agreements.
Okay. All right. Okay. I think, hang on, we got another one. Why does IPU architecture specifically target probabilistic machine learning?
Oh, it does not. It does not. I'm sorry if I made such an impression. Probabilistic models are just inefficient or much less efficient on other architectures. So it's one of the interesting spots very relevant to algorithmic trading. The IPU architecture is not targeted to any specific model. It's very general, it's very flexible. You can do many different things with it, not only probabilistic models. It is targeted towards machine intelligence, but not only probabilistic models. For this specific model, they benefit from the memory bandwidth that we have, because for MCMC you need to make a lot of consequent steps to sample from the distribution. So the model benefits from this 50x memory bandwidth. And this is one of the examples just of the models or methods that are much more efficient on the IPU, not only probabilistic models.
Perfect. And finally, I think we'll just take one more. Can this be applied in games development for future generation of games?
For reinforcement learning, yes, probably, but we do not do any image processing or video processing or 3D acceleration on the chip. It's very different, targeted towards ML, AI specifically.
Wonderful. All right. So thank you very much, Alex. It was a fantastic presentation. Thanks for your time and answering the questions that were coming in. Eve, are we going to hand Thomas? Are you there?
Yeah, I'm there. Thanks, Alexander. So make me briefly present before I hand over to Thomas so that we have a look at the agenda. Give me a second. Here we go. Again, thanks very much, Alexander, for a great presentation. Pretty interesting, and I think that financial industry might be pretty much excited about the speed ups that you have been reporting on. So our next speaker is Thomas Wiecki. I'm pretty happy to have him today on board. Also a German as myself, and he is well known for his expertise in Bayesian modeling. Among others, he is one of the main authors of the so popular PyMC3 package in Python, and I'm looking forward to his talk. And without further ado, I'm going to hand over to Thomas and make him presenter. So, Thomas, let me know if this works. Excellent.
Okay, can you see the screen and hear me?
Yeah, we see the screen and we can hear you. It's all yours.
Beautiful.
Looking forward to it.
Well, thank you so much, Eve, for having me. Thank you all for tuning in. Today, I'm going to talk about Bayesian modeling of COVID-19. I'm Thomas Wiecki, and I thought I'd start by just introducing myself real quick. I did my master's in bioinformatics at the University of Tübingen, and there I got really interested in machine learning and Bayesian statistics and also neuroscience. So that's where I moved then to Brown University to do my PhD on essentially statistical models of brain disorders, and that's also where I got involved in PyMC3. Currently I'm the VP of data science at Quantopian, and as of recently also became more involved in modeling COVID-19. I'm not going to talk too much about that particular involvement. I'm just going to show that at the very end. Rather, this should serve as a tutorial on Bayesian statistics with some very relevant and important data that we have right now. So from that background, you probably gleaned that I'm not an epidemiologist. So take all of this with a grain of salt. I don't really say that this type of modeling is correct or that any of the results or numbers or anything should be trusted. This is purely educational. So it is, however, I think a really interesting case study for several reasons. And one of them is that this is finally the day in the sun for us Bayesians, because COVID-19 and modeling it is really a problem that is particularly well suited for Bayesian statistics for several reasons that I will go into. But it is a problem that, for example, you can't really solve with deep learning, right? It's just not that type of problem. This is a problem where it's about nowcasting, forecasting, being very precise about the uncertainty, time series, right? There's differential equations maybe going on, like all of this complexity, there's prior information. All of this really is where Bayesian statistics is extremely strong. Next reason as well, certainly these models have their flaws, but some of them are useful. And I think that some of them do have this property of being useful for this epidemic, and especially at the very end, that is what I'm going to show, where I think we can really help decision makers make better decisions using this. As I will also show, and this is part basically of the Bayesian workflow, is, well, we start with something that simple and pretty bad, and then see, okay, well, what are the flaws of that model? And then iteratively improve it to become more complex and more realistic. Also, these types of models I put out a while ago and some dashboards around it. And I think that this is really in the spirit of open source. So I and many other data scientists have been criticized for putting out the analyses because it's confusing or many other reasons. But really, I disagree with that sentiment. I think we really should be working together on this, and you put things out there, you get feedback on them, you improve them, other people do pull requests, right? So this is just how this whole thing works, and really the strength of open source, right? Release early, release often, and I think this applies here as well. And then also, I think that technology really is playing a really big role in solving this pandemic. And this has, for me personally, been quite a big surprise, actually, is that I assumed, well, we have the CDC, we have the European Center for Disease Control, we have the Koch Institute, we have all these institutions, right, that didn't do anything but prepare for this type of thing, and then it happens. But then it seems like there were just a lot of things missing. Like, for example, data availability, right? There was just no way that really data was shared. There was the Johns Hopkins data, and they just sort of gathered this from PDF reports put up by the WHO. And then also, well, everyone wants to see what is happening, right? Decision makers need real-time information, but there was just no technology available to build these type of dashboards. And if you spend any time in academia, like I have, you'll know that academics are often not the most technologically versed. And so they're not really in the line of building dashboards, right? And like building interactive things and really engaging. They are in the business of writing research papers, and they're very good at this, but that is a much slower process and something that is not as engaging with the real world. So I think there is a role to play for technologists, data scientists, and modelers to take that into account, right, and sort of contribute our piece to it. And that is what I'm trying to do. So probabilistic programming, why does it make sense for this very particular type of problem? The main thing is that probabilistic programming offers great flexibility to quickly, iteratively build statistical models. And that is really the main point that I want to drive home here, is by showing you three types of models, namely an exponential growth model, which assumes that, well, growth is exponential, which we will see is actually not a terrible assumption. It's an assumption that is provably wrong. And then we will see how a logistic growth model will improve upon that, and then move to an actual epidemiological model, the SIR model, which I will briefly explain. In this talk, I won't really go into the logic of like Bayesian statistics and what probabilistic programming is. Mainly the reason is due to time, but I also hope that just by looking at the code and looking at the results, that you will be able to get an intuition for what it is that this tool allows you to do and why it makes sense to apply this in this context. Probably the other biggest benefit of using Bayesian statistics for this type of problem, but many other problems too, of course, is that we have a very principled way of dealing with uncertainty, right? So, for example, in machine learning, or most other types of modeling, you're often dealing with point estimates. That means you're estimating parameters of your model, and you don't really know how certain you are that those parameters are the true parameters. So what you're missing is, how certain am I in my results? And Bayesian statistics is essentially, from start to finish, a framework that tracks uncertainty in all different stages. So whatever you do, you always have an uncertainty estimate associated with that. And if you imagine that, for example, one very important metric that we're looking at for this pandemic is the reproduction rate, right? RT. So how many people are infected by a single person? And if this is larger than 1, then we have an epidemic. And it's smaller than 1, well, then so that it will just keep decreasing, which is what we want to do. So keeping this reproduction rate below 1 is critically important. And however, of course, you can only estimate that based on data. And if your best guess of that is smaller than 1, well, that's great. But what is the probability that it could be 2 or maybe 4, right? So you really want to know the uncertainty in that estimate, and we will talk about that extensively. And the way this works is that we're never dealing with point estimates, but we will always deal with a distribution of all possible outcomes. So we're not just evaluating a single outcome, but we are evaluating all possible outcomes and assigning a probability to each possible outcome. The other big benefit is that in regimes or in problems where you have few data points, like here, right? So we only have, like, this pandemic hasn't been around for that long. So we're really in a small data regime here. And that makes it very difficult for making inference. But you can really improve your model by supplying informative, what is called informative priors. And essentially that is telling the model certain things that you already know, which it does not have to learn from data. So you're able to instill the model with knowledge that you already have about the problem. And in COVID-19, we have a tremendous amount of, I mean, less than we'd like, but nonetheless, we have a tremendous amount of prior information. We know, for example, from other papers, what likely values of the reproduction factor would be. So we know that the reproduction factor, for example, is not 20, right? Other people have already established that. So we can, from the literature, take these results that people have provided and then instill them in the model, and then even with few data points, make much more accurate inference than without them. And last but not least, there are certain types of models called hierarchical models that I will go on briefly that allow you to pool information across countries. So it is very likely to assume that the disease will spread according to similar characteristics in Germany and in Switzerland or the US, right? Because it's the same virus, you would assume that they're similar, but of course not the same, because every country is different densities, population densities. They have different lockdowns, maybe different procedures, whatever. But nonetheless, there will be similarities, and we are able to exploit these similarities with what's called a hierarchical model. And I will show what that looks like. Throughout this talk, I will be using PyMC3, which is a probabilistic programming framework for Python. It's open source. You can find it on GitHub. And what it allows you to do is, in Python code, you can write down the statistical models by plugging probability distributions into each other. So this will become much clearer when I show it. But basically, it's a toolbox to build statistical models. And that makes it different, just for conceptual understanding, from tools like, for example, scikit-learn. Okay? So scikit-learn, or maybe stats models, is a toolbox of pre-built statistical models. And you can adjust these models to fit to your data, but nonetheless, the linear regression will always be a linear regression, right? You can't change the linear regression in a fundamental way in either of those. They're not they're not like changeable. So, or say a random forest, right? A random forest is very flexible in the types of data that it'll show, but you can't go in and say, well, actually, I want a slight modification of a random forest. It's just not set up in this way. But in PyMC3, you can go a level lower, or you have to go a level lower. You really build your own model tailored to this particular problem. It can be a linear regression, but it can also be a hierarchical linear regression, or a linear regression that is just completely different from anything that you would find in these other packages, and is tailored to your particular problem. And that's what makes it so powerful, is that you can build custom models that solve the very particular data science problems that you're facing. We pride ourselves on having very intuitive model specification syntax. So in the paper, for example, X, the random variable X is distributed according to normal distribution. That would translate to Python code that looks very similar. And that really allows for the iterative workflow, because you're not really doing statistics as much as you're doing code and programming your models, which for me, coming from a computer science background, is really where I want to be. I don't want to stand in front of the whiteboard. I want to hack away in a Jupyter notebook. The next best thing is that there is a so-called, well, what I call an inference button, and that is an automatic and powerful inference method for any model that you do. And those approximation algorithms that we will be talking about are Markov chain Monte Carlo. And the reason you need them is that in order to get these uncertainty estimates, you need to run your you can't just evaluate this. You need to do inference. And fortunately, this inference is happening completely automatic. So you can just dream up any model that you want, hit the inference button, and it'll give you the answers in, I would say, 9 out of 10 cases. In those 10 cases, sometimes you need to do a little bit more extra work and figure out what is going on. So these algorithms are very powerful, but they're not magic. So they can and they do fail. Last but not least, it's built on Theano, which makes everything nice and fast, while still being written in Python. But actually, behind the scenes, it's being compiled down to C and then compiled to a library. So that makes it nice and performant and gives all kinds of other benefits. The first model that we're going to look at is an exponential model, and this is actually not a terrible model. Early on in an epidemic, we know that growth is exponential. That's sort of the definition of an epidemic. And what it is really just a linear term where similar to a linear term, but where the x variable time happens in the exponent. So we have our function f of t, and this will describe, so over time, right, we will describe how many cases we have. So this is exactly the type of problem, right? If you think like, oh yeah, on the first day you just have 20 cases, and then a few days later you have 40, and then you have 80. So this doubling is really what's so incredibly dangerous. And I think this is really what caught us off guard early on. I mean, now we're like, I think pretty solid, but just how quickly this thing starts to take up steam, and then just growth is very explosive. That is what makes these epidemics so dangerous, right? It's like, oh, well, we just have 100 cases. That doesn't seem like a big deal. And then a couple of days later, you have 200 and then 400. Well, that still doesn't seem such a big deal. But again, this exponential growth is really what can make these numbers explode very quickly. And that is best described by this function here. So we have an intercept term, A, and then we have our growth rate, B. So if that is larger than 0, that means that we have this exponential growth. Then we are talking about an epidemic. And then T here is the index point. That's just the way the formula works. And now what we will do is build this model in PyMC3 and fit it to data. So for that, I'm going to switch over to this notebook here. A little bit. So I'm importing a bunch of stuff, and then I'm loading in the data. So this is data from the WHO, and it is essentially just how many cases are there every day in time for all these different countries. And also I should note, I created these notebooks quite a few weeks back, so the data is not up to date. I plan to rerun it, but actually it's not a current focus. I will show what the current focus is. These are more historical, but they are still illustrative. So here we will look at old data, where the model still holds. Today they don't hold, so they're even more wrong today than they were back when I created them, just so you know that this is out of date. Okay, so we have data for these, and we're just going to focus on the S1 now, and just plot the number of confirmed cases that we have over time. And you can see this ends in March, so quite a bit old. But in this period, as you can see, we really have this exponential growth. So very quickly we're at 10,000 cases, then we're at 30,000. So yes, it's just blowing up. Now these days it leveled off, which is exactly what we want, but that is due to all the measures that we've taken. Right? Okay, so now we want to model this. How do we do that in PyMC3? So let's look at the code. The first thing I'm doing is I'm just taking, okay, my time value, and I'm going to offset this to be from the how many days since we had 100 cases. This is just something that makes our life easier. It doesn't really matter. And then here we have the number of confirmed cases. So this is just for every day. There's a time series of this number on the y-axis. Now this is what that model looks like in PyMC3, and I hope that I can explain what Bayesian statistics does just by looking at the code. So let's give it a shot. Here, the first line is just boilerplate code. You don't really need to pay attention to it. What it's doing is it's instantiating a PyMC3 model class and then binding it to this model. And this is purely for bookkeeping. What it says is everything that happens indented under here is going to be tied to this model object. But really, this is every model will look like this. What gets interesting now is below indented, where we are now specifying our model. And every model starts the same. We start by defining our parameters. As we've seen in the descriptive slide, there is an intercept, there's a slope, and from that we can compute our growth. So, okay. The other thing I mentioned is that we're dealing with priors, right? So usually in a, let's say, a maximum likelihood model, you would just say A is a parameter, right? And it can take any value from minus infinity to plus infinity. Potentially, you just start somewhere, you run an optimizer, and then you find that one parameter value that best explains the data. Here, things work differently. Here, we are specifying a prior distribution, which is informing my expert knowledge or not so expert knowledge about what I think plausible values of the intercept are before I've seen any data. So this is where we can instill the model with data we have from the literature. And sometimes we might not have a lot of information, right? In those cases, we will be having priors that are very wide and are not constraining the model, right? So we could have a prior that even says, oh, every value from minus infinity to plus infinity is equally likely, and then we get back the maximum likelihood estimator. But here now, we do have quite a bit of information. For example, we know that the intercept, basically where this starts on day 0, because we're offsetting everything to be how many days since we crossed 100 cases, well, then the intercept is going to be very close to 100, right? So because that is just how we set it up. So that is why I'm defining a prior distribution, normal distribution from the PyMC3 namespace. The first parameter is always a string, which is just the name of the parameter. This will always be the same as this over here. It's a bit of a technicality that you need to specify twice, but you need to do that. So the first parameter is always the name. And then we give it a mu. So again, as I said, well, because we have set it up so that it starts at when the cases cross 100 cases, it will be close to 100. But I mean, on that day, it could have been 150 cases, for example, right? So we do have some uncertainty around this, and I'm going to say the standard deviation is going to be 25. So that's just the choice I make as a modeler. And you might disagree and make different choices. That's fine. You can just go in now and change the model and run it with price that you think are more appropriate. And then the slope is essentially how quickly it grows exponentially. And from early estimates from the literature, we know that essentially it's going to double every 3 days. So that is a growth rate of 33%. So that is what I'm specifying here. So the mean is going to be 0.3. So this is the value that I got from the literature with some standard deviation, because we do want to estimate this parameter and don't want to fix it because it could be different for different countries. Now that I have defined my parameters, all I need to do is plug it together according to the formula that I showed you before. So we have our intercept, we have our slope, and we have our data on the x-axis, how many days from 100 cases. So this will just now return a vector because this is a vector, so it's automatically broadcast, vectorized. And then the last thing we need is our error term. We know that the error of this is going to be positive, so that we're choosing half normal, which is just a normal distribution that doesn't have any mass below 0. And then we need to specify our likelihood function. So this tells me, okay, how is my data distributed? And here I'm choosing actually the wrong distribution, but this is from older code. Here I'm using a log norm distribution. This should be a negative binomial, but or a Poisson distribution because we're dealing with counts. But that is what it's here. So this is something that I should improve in this model, but this is what I started with. Either way, log normal is not a terrible choice. At least it specifies that, well, there can't be negative cases, right? They can only be positive. That's why it's log normal. And then the mean is we need to take the log of that. So this is where we now have this is what our prediction is. And then we have our error term. And then we need to specify what is the data that we're actually modeling. So this is where the observed keyword argument comes in, and where we plug in this array from up here, confirmed. So this will just be the number of cases, which is also a vector, right? So essentially what this is doing then is saying, okay, well, we have our model. This is going to be the prediction. The prediction goes into the likelihood, and it's being constrained by the data or trying to explain the data. So hopefully that makes sense. And then the only thing we left to do is actually run the inference. So as I said, this just specifies the model. Now we want to run the model. So for that, we just call pm.sample, which runs the Markov chain Monte Carlo estimation algorithm and returns a trace. This trace is what we're interested in, and it is the samples from the posterior. So what that means is, as I said before, the result of this model run will not be a single value for A and B, right? Instead, what we're getting are distributions over A and B. We will look at that in a second. So when I call this, it just samples very quickly. Here, I'm also asking the model to do predictions. This is from the posterior predictive. This will become clear in a second, but essentially we're just, asking the model to predict. And then I can call trace plot to now plot my posterior distributions. Hopefully here, it'll become intuitive what these posterior distributions are. Here you can see now the posterior for A, B, and our error term. For A, we actually see, well, we thought on average that it's 100, that was our prior information, but now that we have seen data, we actually assume that the intercept is most likely going to be 115, right? But again, we don't just have single values, we have a distribution of values. So we say, well, most likely it's going to be 115, but also 110 for the intercept is also going to be quite plausible. And 105, well, much less plausible, but we can't rule it out. But very unlikely that it's going to be 100. So this is what this is telling us. And again, we're not dealing with a single outcome, but we are placing a probability, which is what's on the y-axis, right? So parameter value on the x-axis and belief or probability on the y-axis. We're assigning a probability to every possible state of the model. The same for our slope, b. So here you can see that it's quite close to 0.33, but actually higher. So early on in the ES, we had a spread that was faster, slightly faster, but nonetheless, these are important differences than what was suggested in the literature. But certainly, the original value is still, well, fairly close. But again, we can almost rule out at this point that it's 0.33. We think that it's higher with quite some certainty about that. And then EPS is just the error term. We don't really care too much about that. So this is just what I'm getting out of the model. Really, what we're interested in is what are the predictions, right? So now this is where the posterior predictive comes in. So in red, I have the data of the US, right? So this is US data over time. Now I have offset it to how many days since we crossed 100 cases. And on the y-axis, we have how many cases have been confirmed. This is the exponential growth. And this is the fit of the model in gray. And well, because we are starting with probability distributions and getting our posterior probability distributions, our predictions will also be distributions. So we don't just have a single prediction, we have many, many, many predictions, one for every sample from our posterior. And this gives us also uncertainty in our forecasts or our predictions, as you can see here. So first, in the beginning, we're fairly confident that this is the band around which this happens, but the further into the future we go, the more uncertain we are. And there are a few things he can also say. So we know, okay, well, it's getting more uncertain, but we also know, well, actually, it's a pretty good fit, right? So the exponential, despite how very simple this model is, it is tracking this curve pretty well up to that point. By now, it's completely broken and it won't fit at all, and we will see a case where it already doesn't fit. But for that time period, it is just visually not a terrible model. Now we can do one better and exploit the fact that we know that countries have similar characteristics, right? So if we're looking at, let's say we are fitting the same model to Germany, the US, Italy, Poland, all different countries, right? These parameters will be similar, right? Because it's the same disease, but they will be different. So we can exploit both of these, the similarities and the differences in a certain hierarchical model. And the way this works is that every country that we are modeling, we will assume has its own distribution, right? So we can think of every, let's say this is the slope, how fast does it spread. For Germany, this is how fast it spreads for the US, and this is for Japan. These will all be similar, and we model this by assuming that these values actually come from an overarching distribution, the group distribution, which specifies the group mean. So on average, we might think, well, all countries on average have a reproduction rate of 33%. And this basically will constrain every country to be, when in doubt, when we're not sure, right, we want to be err on the side of 0.33. So what this is essentially doing is saying, okay, we allow every country to have its individual parameter, but at the same time, we estimate the similarities, and that will help the inference tremendously. And one example where this becomes relevant is if you imagine that you have a country like China or Italy or South Korea, those are the countries where the pandemic spread very early. So we have lots of data points, and we can be very certain in our estimates because with lots of data, we have higher certainty. These will inform our group mean estimate quite a bit. But then we have countries where where the disease has only spread very recently. So we have very few data points. If you were to fit an individual model to a country, we have only very few data points. So obviously, estimates are going to be extremely noisy because with, say, let's just say 5 days, right? You can't really estimate these parameters all that well. So the uncertainty will be huge of that forecast. However, if we are leveraging that data that we have from these other countries that have much more data, then we can get much more accurate forecasts even for those countries where we don't have that, just because we leverage that information. Okay, so what does that model look like? Actually, it's quite similar. We have our boilerplate code, and then we have our intercept. But now the intercept is not just a single intercept, it's actually an intercept for n number of countries, all the countries that I want to model. And the mean mu is now not, say, 100, as I specified by hand before, but it's actually another parameter that I'm also going to estimate. And that is the group mean and the group standard deviation. And I'm also placing price on that. So basically, we're just, implementing the structure right here. And then we're doing the same for the slope. And then all we need to do is just create a likelihood function for every different country with the growth rate that we have. Now we're indexing because we have not just one, but many countries. And we are, so here we're just looping over every country. So for every country, we're creating the exponential growth, and then we are creating the likelihood function. And then again, we don't need to do anything. We just run the inference and get our results. So here we get our posteriors for the different ones. And I think I have it in the back of the slide, so I'm going to switch back. But that is what the hierarchical model looks like conceptually. And so actually, I don't have the results in here, but I have them for this next model. So one thing you can see, for example, for another country like South Korea, unfortunately, I don't have that plot here, which is a bit of a bummer. But so I'm going to go here. So this is already the next model in gray. So ignore the gray part, but let's just look at the red line, right? So the cases in South Korea start out very exponential, but then they flatten out, right? Because, well, they took countermeasures, and those countermeasures are working at slowing the spread. And this is what it looks like for many other countries, right? They have this early ramp, and then they are getting back together, and things are slowing down. And that breaks the exponential model, which is great. We want this model to break. So obviously, this model is also ridiculous because, I mean, nothing in this world can keep growing exponentially. At the very least, it will be limited by the number of people we have in each country. So there's many problems with this model. And the logistic model is basically one step better. It's still not great, but it's just fixing that or improving upon that problem that we have with a with this unrealistic assumption of uninterrupted exponential growth of the previous model. So we have a saturation, and well, it's really just a logistic. If you look it up, and it has one more term, the carrying capacity, which is where it sort of plateaus. And I'm not going to show the code. It's very simple. You just can build this model in PyNG3 as well. And then here you can see basically the predictions in gray for South Korea. So we have this carrying capacity that we estimate. And in red, again, the data. And also here you can see actually, well, this is not such a great model either. So already, and it continues to go up quite slowly, but you can already see, well, actually, it's not completely just staying flat as the logistic model would predict. It is still going on, and that is a problem of this model. Again, no model is perfect. And also then I implemented this for the as a hierarchical model for some selected European countries. And here you can really see why tracking uncertainty is so important. If you were to just fit the best fitting line, you get something maybe, let's say for France, and again, this is like old data. So by now it looked quite different. You probably get something that levels off here. And then you think, oh, okay, well, great, 5,000 cases. Well, again, don't take any of these numbers seriously at all. But let's just assume that this would be properly calibrated, which it's not. Then we would say, okay, well, 5,000 cases and it'll level off. Well, fantastic. Well, not really, because our uncertainty in this carrying capacity is huge, right? Could also be 15,000. So we have all this uncertainty in our forecast, which we would ignore if we didn't track our uncertainty properly, like we're doing with Bayesian statistics. In cases where we already are further along in the curve, like Italy, well, there we have much more certainty where this will level off, right? And of course, the other benefit, the point that I made before, countries like Italy, where we have more data, we will apply what we're learning here due to the nature that it's a hierarchical model to these other ones. And that could allow us to make better inference and constrain the inference also of this carrying capacity. So this is already essentially applying what it's learning from other countries with more data to these with fewer data points. But nonetheless, the uncertainty is still very high. Cool. Then if I still have time, I'm just going to show very briefly the SRR model, which is an epidemiological model. Just 3 compartments. We assume that they are susceptible, which at the beginning is the whole population, who can get the disease. Then with a certain rate, people become infected. Once they're infected, they are infectious and can infect other people. And then after a certain time where they have been infectious, they will move into the recovered bucket, and with another certain rate. So these beta and gamma are the parameters that are part of the SRR model. And what is cool about this model is that it gives you these much more realistic curves, right? Before we had either an exponential curve of growth or just a statistic curve of growth. Here we can take more information into account and model the dynamics of the disease much more accurately. So here you can see, for example, that the number of susceptibles starts at 100%. The whole population is susceptible. Then as people become infected, the number of susceptibles goes down. Then as those people become recovered, the number of infected people goes down, and the number of susceptible also goes down until eventually you reach what is herd immunity, where everyone is recovered and everyone is immune. If that is the case, there are all kinds of extensions to this. For example, now we seem to have pretty conclusive evidence that you might not stay all that, that you can get reinfected by COVID-19, in which case there could be another term where you go from recovered back into susceptible, and then you can change this model. So this model then is described in terms of differential equations. And we can solve these in PyMC3 as well. And I'm also just going to show this very briefly because just to show that it's possible, essentially. So this is work with Kevin Systrom, who has built this original model. And what we're doing is we're specifying a Python function that is our SRR model, and it's just describing the differential equations. So this is just the math from the differential equations. We have our beta parameter, just times by the number of susceptibles, times by the number of infected. That's the interaction between the two, divided by the number of total people in the population. We have our recoveries, and then here is the differential equations. Really, this is just copying the math and code from the known formulas from this type of model. And then we can build our model. We again place priors and specify our parameters. The thing that I want to show here is that in PyMC3, there is something that Google Sum of Code student contributed, which allows you to solve differential equations inside of your Bayesian model using this differential equation class. And it takes the Python function that we just looked at and a whole bunch of other stuff and then essentially you can run Bayesian statistics over an ODE, and then get your posteriors back, which is cool. And then also you can also plot the number of total cases, what the model predicts. So this is essentially as before, but now the curve here in the background, our predictions are coming from the SRR model, which is a much more plausible model than the other one. And we can plot things like, okay, well, in New York, what is the number of susceptibles starting at the population of the state of New York? And you can see, well, it goes down. Again, we have our uncertainty, we represent by width here, and we have our infecteds go up and our recovered go up as well. So the model can just now, model all these different dynamics of this disease. So then before I close, I just want to show something that I have contributed to, but really Kevin Systrom is the main guy who worked on this, is the website rt.live, where we're providing daily updated numbers of the effective reproduction rate. That is the critical quantity that we want to track and keep below 1, so that we know that we have things under control. And here you can see, okay, for every US state, it's US only so far, for some technical reasons or data availability reasons, really. It's actually pretty well for most of these, but you can also see the uncertainty, right? So this, again, so this is using PyNC3 under the hood, and models similar to ones that just showed the SRR model. So Wyoming, for example, well, it seems to be below 1, but really there's there's a shockingly high probability that this estimate could be completely off, and it could be 1.3, which would be much more problematic. And then on here you have, over time, how does it change? When was there a shelter order or lockdown? When did they reopen? So you want to, every day you want to track this value and make sure that you're not basically, exceeding these thresholds. And again, you're seeing the nice uncertainty bands around them for every state. So yeah, that's all I had. There's some information on how we're computing this. Definitely check it out. So with that, I'd be happy to take questions.
Thank you, Thomas. Fantastic, really clear presentation there for everybody. Quite a few questions have come in. Essentially, do you use mathematical calculus, matrix calculation, or calculus, or computational, e.g. SciPy optimized methods to compute argmax equations? For example, finding your slope coefficient. In other use cases with more data at hand when building your library.
I'm not 100% sure I understood the question, but I think I did. So the question is asked about argmin, so optimization, to infer the parameters of the model, and that is not what's happening. So usually you could build these models, right, and then just have a function, and you want to minimize the error of between your model prediction and the data, and then you would just plug that into an optimizer from, say, SciPy. So that's not what's happening here. Here, because we don't just want single parameter values, we want distributions. So we can't just run an optimizer. Instead, what we're doing is we're running a sampler. The sampler works quite differently from an optimizer in that it's not just finding the best value, but it's sort of walking around in this posterior landscape of parameter values and just giving me those parameter values that are more likely, more often. So this is Markov chain Monte Carlo, and maybe I can just link to a blog post I have on that, which explains how that sampling algorithms work. So twiecki.io. There's a bunch of stuff that explains this, but the one that I'm referring to is called MC sampling for dummies. So this basically explains really intuitively how the sampler works and what makes it different from an optimizer. So I hope I didn't completely misunderstand. That's quite possible, but that's.
I think that's correct. Yeah.
Right.
So so in PyMC3, do you always need to specify the model structure, the mathematical equations with the features and parameters, or can you also learn it by the data itself?
Yes. So you always have to specify the model. And you can specify that there are certain types of models that are quite general. For example, let's say the Gaussian process is something which is called a non-parametric model. And that is still, you specify exactly what type of model you want. But what you're specifying is, I want something that is very flexible and can fit all kinds of different shapes. Just looking for some plot because that will drive that point home. Here we go. Oh, no, that's not right either. Okay, well, while I bring that up, so in general, the actual answer is no, you can't. You always have to specify it. That is just the nature of statistics. There are models that you can fit that, or there are models that are on the that are prepackaged, right? That you can reuse, but generally this is more for, okay, I have a very particular problem that is not solved by a random forest or a linear regression, but I have more information, more structure in my data, like let's say hierarchical structure, and then you build a model tailored to that. One other thing that I would say is there's a package called Bambi, which just makes it much simpler to build hierarchical models. So here you can specify, if your model is a regression type problem, and it can be a hierarchical regression, then you can specify your models not in like line by line, but you just say, okay, I have on my right-hand side a dv variable and two coefficients that I want to estimate, and then this makes the whole process much simpler. So yeah, if you want something like mixed effect models that are linear regression based, then check out Bambi.
Great, thanks so much, Thomas. How robust is the model for hidden variables? Carl is asking.
So hidden variables, well, essentially they're all hidden variables. So let's take this model, right? So the parameter, or let's go here. So this is the model specification again.
Oh, sorry, he said afterwards. How robust is the model for latent variables, hidden variables?
Yes, great, okay. So, very robust, because maybe all parameters that we are estimating are latent. So this is maybe how Bayesian statistics works, is we specify latent parameters, right? So we never observe the intercept, or we never observe the slope. So these are latent, and we want to infer them based on data. So really, the one way to think about this is as a generative model. So we have latent, unobserved, hidden causes that we assume relate to our data in a certain way, right? So from these hidden causes, we generate data. That's one way to think about it conceptually. That's not what's happening under the hood, but that's a good way to conceptualize it, is, okay, we're thinking about the world from hidden causes down to data that we don't actually observe. Once we have the model specified, well, we don't observe those latent parameters, we observe data. So then we need to work backwards. What are the most likely latent causes to have generated the data that I actually observe? And that's what Bayes' formula does, essentially. It's inverting the generative model that you have described.
Wonderful, super clear. And then somebody asking, why do you sometimes use the NumPy log function and at other times use the pmath-log function?
Yeah, that's a good question. So this is a technicality. So under the hood, actually, it is detecting that it's using a NumPy function and then it's converting it. So it is the same thing. So it's detecting that I want to use the log, and then it's converting that to pm.math.log. To make it clearer, I should have just written this, because then it's clear, like, oh, this is not the NumPy log function and there's no magic happening. Yeah, so for certain NumPy functions, it'll work just because it has some magic built in. But yeah, it'll get converted to Theano expressions, and this makes it clearer.
Is it possible to estimate parameters for stochastic differential equations with PyMC3?
No, we don't have support for that. I'm pretty sure. Those are totally, like, differential equations are already complex, and then we add SDEs to the mix. Things get quite crazy.
Okay. I mean, we had a couple more questions as well. I think we're sort of running pretty much okay for time. So where can we access, I think, the COVID-19 data? Is that probably from WHO, I would imagine?
That's right, yep. So there is a GitHub repo that has daily updated data. So GitHub Johns Hopkins. So this is not the source, but I think it has a link to the source. So this is basically a data set which just updates it automatically. But really, one source is this repository, and apparently they moved it. So this is where I think I started out using it. But now there are better data sources available. But yeah, this is one. Then covidtesting.org or something is another one, which has also not just data on cases, but also how many people were tested. So this is a critical thing to know, is if you only test 10 people, well, you can't get more than 10 confirmed cases, right? So there's all these biases in the data that we need to correct for, which is what we're doing with these much more complex models that underlie this website. So one of the big problems with what I just showed is that it's ignoring so many complexities hidden in the data that you need to know about. And this model does a much better job. But yeah, so there is like all kinds of different data sources, and this repository based on the WHO data from Johns Hopkins is a good one.
Lovely, thanks. And obviously, as per usual, loads of questions saying, could they have access to the notebook that you've shown? I've already put out, I think, a couple of times access to your, there's a PyMC3 GitHub repo. Where is this one? Are you able to share that? Or
I have it up on my own, but that is older. So Wiecki COVID-19 has this model, which isn't quite the one that I showed, but similar enough. Okay. Yep, so you can just check it out here. And this is the hierarchical model.
Lovely.
I haven't run this in a while, so it might break actually. But just for looking at the code at least, you can do that. And I also will upload these ones. But yeah, so as I said, I'm not really developing these further just because the work is going into these more realistic models.
Got you. And then finally, if there is a future forward-looking question, do you have any expectation when PyMC4 will be released, SpyPaddle?
Oh, thank you for asking that. Yeah. So we actually have an alpha out already. So there is the repo. So it's just PyMC-dev/PyMC4. Currently, it's not. Oh, actually, there are some. And you can use it, and it has a fair amount of functionality already. So you can sample and you can build your models. I wouldn't. It's still very early days. And it might break, but this is what it looks like. So hopefully this looks similar to what you would expect from PyMC3. The only difference is that yield keyword argument. But other than that, so you can build, I would say, almost all of the models in PyMC3. And then, so here you again have the observed keyword argument. and then the sampling is still a bit janky. But yeah, so it's making good progress, but I wouldn't hold my breath to have something stable anytime soon. I would also add that personally, I have been quite dismayed by the sort of discontinuation of Theano, but now I sort of changed my mind a little bit. One thing is we've taken over maintenance of Theano, and Theano is actually very stable. It has been for a long time, so a very mature project. And as long as we keep it going, I think it'll be a really good base for PyMC3, because one of the things that we're noticing with PyMC4 is TensorFlow probability and TensorFlow 2 are moving at such a breakneck speed that they keep breaking our code and we constantly need to rewrite it. So you would think that that's amazing, right, to be on something that is continuously improving, but actually it's quite painful because it's breaking things all the time. And also PyMC4, despite like all the fanciness of TensorFlow 2 and the hundreds of thousands of developer hours, still way slower than Theano. So Theano is simple, elegant, it's stable, and it's fast, which is everything we need for PyMC3. So that's why I'm still very excited about PyMC3, and most of the development is still going into PyMC3. So that won't go away, and will be continued to be developed and continue to be improved. So definitely would still suggest to jump in there and not wait for PyMC4.
Wonderful. I got to say thanks so much, Thomas. That was awesome presentation. Yves, do you want to kind of take over?
Yes, I will. Let me present a second. So I'm going to show the screen. Yeah, and first of all, thanks very much to our two speakers of today. I really enjoyed both of the talks from Alexander and from Thomas. Really insightful. I hope you enjoyed it as well. And I want to encourage you that you reach out if you have an idea for a talk. And it doesn't have to be like a full-fledged, let's say, 45-minute talk. If you have something interesting, a snippet of Python code that is said, well, we're working on that, and this could be of interest to others, so feel free to reach out. So not only full-fledged talks, but also maybe shorter ones, or what is typically called a lightning talk, maybe 5 minutes or 10 minutes, where you introduce, I don't know, an exciting new package or a little approach that they said it might be useful to the community. Feel free to reach out. We would be happy to discuss, and also forward like invites that you receive from Meetup to your colleagues, to friends that you know might be interested in Python for finance. And having said that, thanks for tuning in. We are up for some other virtual meetups. Watch out for the information. Thanks to Jason as well, Refinitiv, our sponsor here in this regard, as usual. And I can only say, stay safe, take care, and I see you soon for the next virtual meetup. Bye-bye.